we start, I would like to announce the TAP Graduate Student Research Prize. So this year it goes to An Ho Chan on his research project halfway to radiate other insight into Rossby wave instability. So I don't know if An Ho is here, but maybe we can speak. So An Ho will be presenting on March 3rd for his prize. So please come to listen to that talk. And for today, just a second. Okay, so it's a great pleasure to have Yu-Dai Tsai for our TAP Colloquia. So Yu-Dai got his PhD from Cornell. He was a postdoc at Fermilab, UC Irvine, and now at the Los Alamos National Lab. Yu-Dai is known for his work in combining particle physics and astrophysics. He published multiple papers on Nature about detecting dark matter in the solar system with space quantum sensors. And he's also involved in multiple NASA programs to make these experiments reality. So very impressive. And today he's going to tell us about this work. Please take it away.
Yeah, thanks a lot for the introduction. So today it's a very nice opportunity to talk about our exploration of the elusive universe to detect dark matter at the precision frontier. But really, this precision is more on the observational side combined with the measurement side in terms of something that are very practical. Actually, let me turn on this, my own. It's very practical for us to consider. So there's a lot of practical application, but also it can improve our understanding of the fundamental physics. And by the kind of middle or towards the end, there will actually be a new dedicated mission that I want to do with NASA to try to find dark matter gravitationally in the solar system. So let's get into it. So here is a summary of the strong probes of the elusive universe. So I come from a more like a particle physics background. So above this is a slide that kind of summarizes a lot of the particle physics probe, but increasingly there is exciting searches using telescope, direct detection experiments, and large observatory. And we have a lot of goals to try to probe high energy theory. And it's still very exciting, and we'll continue to go on the collider to study collider and search for the fundamental high energy theory. But equally exciting is to go to the elusive direction, meaning probing the content of the universe that are weakly interacting with the rest of the stellar model parts. So the y-axis is the coupling strength, x-axis is the mass, and really this group of elements are extremely important for the evolution and operation of the universe, and a major effort is to probe neutrino, dark matter, and gravity. And since we already found neutrino and understand gravity, the next big thing is dark matter. But because these are all elusive, there are many methods that you can probe all three of them, kind of in different aspects. So I will also mention a little bit about that. And really, because it's so hard to probe these things, you need a comprehensive effort in all fronts. Like neutrino, you study in cosmology, astrophysics, and collider. Similarly, for dark matter, that's also what we have to do. And today I will talk about how we can use planetary study, quantum sensor to study these type of subjects. And you've already seen this many times, so I will not get into too much detail. But the idea to show this pie chart is to say that most of the universe we actually don't fully understand, but they govern the evolution, including dark energy, dark matter, and neutrino. You don't even see neutrino here, but it's still very important. And we will not stop until we understand all of the pie. But let's also look at what do I mean by the precision frontier. And it's a little bit wordy, but so please bear with me. So the precision frontier, what I mean is that you have very high precision to track times or to keep us safe. For example, OSIRIS-REx mission that is led by the LPO is to track this potentially hazardous asteroid Bennu. And we can actually achieve 1 meter precision for the object that is around AU distance. So it's extremely high precision. So roughly speaking, the fractional uncertainty, if you divide it 1 meter by 1 AU, is 10 to the minus 11. So you have 10 to the minus 11 high precision. So I call this precision frontier in the measurement. Kind of in any astrophysical planetary measurement, this will be the leading precision. Of course, you can track planets equally or even better. And these are all I consider the precision frontier in terms of measurement. And secondly, you can also keep time very nicely. So you lose roughly 1 second per 10 million year using this NASA Deep Space Atomic Clock. So why do we develop that? I will tell you more, but basically it's to navigate, because only when you can track time very well, you can navigate well, because the way you measure distance is you send a signal from A to B, send a light, for example, from A to B, and wait for it to come back. So keep tracking of time is also a way to keep tracking of distance. It's also a way to navigate. So deep space atomic clock is extremely important to keep us on time and keep us travel well. If in the future we want to go to Mars, this would be very important. So there's a lot of exciting. And the theme of the talk will be try to maximizing the connection between all these different aspects and try to move forward to study very difficult topic. As I will tell you, there will be a ultimate goal I want to reach, but it will be kind of in the middle and end of the talk. But please stop me anytime if you have any questions. Awesome. So first we'll talk about dark matter and solar ultra precision astrometry, which I'll learn a little bit. But we'll learn from both Vera Rubin and Albert Einstein. Sorry, this is a little bit blocked, but this is Vera Rubin, who is looking at not the solar system, but looking at the galaxy to find the dark matter. And Albert Einstein is actually looking at the solar system. Actually, the astronomer at that time is looking at the solar system to confirm gravitational theory. So today we'll kind of combine these two elements to try to find dark matter in the solar system. Okay. Good. So let's first get a quick review of how much do we understand how much do we understand dark matter? How do we know about the existence of dark matter? So the existence of dark matter, we already understood in very large scale. So coming from the galactic scale, we have galactic rotation curve. And then going to the bullet cluster level, we understand in the cluster merger, there is this gravitational interaction of dark matter. And then there's large scale structure, which is even larger. So all the way from the galactic scale to, let's say, millions of light year for the merger level. And then going to the billions of light year to the large scale structure. The people here you guys are very familiar with this, using the simulation and the large scale survey. And finally, the whole universe, the CMB, we have confirmed a dark matter interaction in all these levels. But first of all, it's only gravitational. And secondly, we have never found dark matter going this direction. So we have never found dark matter in the solar system or smaller scale, first of all. And we have never detected any interaction beyond gravity. So these two things are the most important observational thing that we need to achieve in order to better understand dark matter. And today we'll try to address both of them. So far? Awesome. So why haven't we seen dark matter in the solar system? The answer is very simple, because it's very difficult. So, but why is it so difficult? So first, let's look at how Professor Rubin is understanding dark matter. So you look at the rotation of the galaxy. This we all learn very well. Then you find out the thing's outskirt is moving faster here than this one. So now you can reconstruct what's inside of this galaxy And you found out that there's more matter here than this one, even though they look very similar. So then, for example, in the galaxy M33, you can reconstruct its matter distribution using the velocity, virial velocity, or the velocity of this object. By looking at the velocity, you can reconstruct the matter distribution, and you find out it's different from the expected from the visible disk. So that's how we understand dark matter. Right? But why don't we do that in the solar system? Because in the solar system, there's so few dark matter comparing to the solar mass. In fact, let's do a quick estimation. The galactic average, let's use 0.3 or 0.4, either way is fine, GeV per centimeter cube. The dark matter average density, if you consider galactic level, is 10 to the minus 18 comparing to the solar mass in this region. Of course, this is just a rough density to compare to, but you can see it's extremely difficult to find dark matter in the solar system, pure gravitationally. And that is exactly why we haven't found dark matter in the solar system, right? Gravitationally, it's almost impossible to see it, but it's not impossible, which I will tell you why it's not impossible. Because, and there are many different ways. So people have tried our best to use direct detection to find dark matter. But what if we're in a void? Then it will be extremely hard to find dark matter. And what if we're in an overdensity? Then it will be much easier to find dark matter. So the best way to find dark matter, because we only know it's gravitational interacting, is still through gravitational interaction. Although it's hard, we should think about how to do that. But of course, if you have any other interaction that you can detect wave-like dark matter using a clock, or you can use this large-scale detector to study collision of the dark matter with nucleon or with electron. And these are all very important. But first, let's also think how to study it gravitationally. Okay, so here is how we go beyond velocity. We study the detailed trajectory, just like what Einstein and astronomer at that time told us how to do it. So for the very simple Newtonian gravity, so here I define the semi-major axis as A. So this is the kind of the elliptical orbit. I define the semi-major axis as A, semi-minor axis as B. Eccentricity, of course, is how spherical these orbits are, and it's defined as this way. So we found, since our gravity is not just Newtonian, it has generativity. We found out that there is an anomalous precession, meaning every time after each orbit, there is a different angle. So you can see going from here to here, that is called precession. And this is one of the first ways to confirm generativity, right? So we know this very well. Any questions so far? So what we do is we consider what if there is local overdensity of dark matter. So here we have a very simple assumption. Later on, I'll tell you this assumption is not the most sophisticated, but let's start with this one. Let's say we have a constant overdensity like a ball of dark matter in the solar system around the sun. What would its effect be? And also another way to another similar configuration is you have a shell of dark matter only covering the orbits. And these two things actually give you the same effect in terms of effects on the orbit, because this will give you, just using the classical mechanics, you can derive that this will give you a force that is proportional to the radial direction. Of course, it's attractive because it's gravitationally, so you have a force going inward, but it's proportional to the density of the dark matter rho zero and proportional to R. So the larger the R, actually you have larger the force, and it's pointing inward. Any questions for this one? So you can derive it through classical mechanics. And of course, there is another 1 over R squared force, but this one is indistinguishable from the sun. So this is too small, so we neglect this. Also, this one doesn't induce precession, because as we say, 1 over R squared, no precession. So there's no precession, so you need something beyond Newtonian. So this one will give you a precession. Okay. And the induced precession is proportional to rho 0 times a to the third times this vector. Okay. Awesome. Any questions so far? This is the precession. So we can use the precession as a proxy to probe this rho 0. Of course, ultimately, when we do the analysis, we don't really care about the precession only. We care about the whole trajectory. But I did an analytical estimation using the precession, and my colleague at JPL used this to do the analysis, and we got very close results. So it seems that precession is actually a great proxy to analyze this problem. Semi-analytic. Okay, so what are the data that we're using? So this is the general method. What are the data we're using? So we'll use all the data that basically University of Arizona is very great at tracking. So we have the space mission, which is OSIRIS-REx, which I will explain more. We have the optical data from Pan-STAR, which is run by Hawaii, but also I know here there's also some involvement. And we also have the radar data from Goldstone. Used to be we have the larger radio telescope, but it doesn't exist anymore. So now we have the radar from Goldstone. And in principle, we can analyze all the asteroids in the solar system to constrain dark matter over density. So here, let me say it again. It's a little bit over density above the galactic average, then you can detect it. If it's completely flat, it will be very hard to detect it. There is still some proposal to detect that, but that's not so easy. You need at least a little bit over density to detect it. But I will tell you these are predicted, so no worry about this. I will tell you more about the sophisticated prediction. But anyway, you can analyze all the asteroids in the solar system for their analysis, and it's a very data-intense analysis. So if people here have very strong data ability, it would be great to collaborate. I'm not so strong in analyzing a huge amount of data. I'm learning about it, but definitely some more stronger people who already have the expertise would be great to participate, to collaborate with you to learn about this. But theory input is also important to find out which one is the one that we should study. Okay. So these are all the asteroids and planets, and also any object. But of course, the clean one are the better. So asteroid and planetary defense. So why is this so important? I don't think I need to say this here, but asteroid tracking is extremely important. Yeah, please go ahead. Yeah.
You're saying like this orbit precision is giving the estimate of dark matter density at the center.
Over density.
Over
yes.
density.
Constraining over density. Yeah.
So, but we can have the similar like precision because of GR effect. So
Absolutely.
how we are not like confusing between.
Absolutely. So this is an excellent question. I will cover about that. But let me give you a quick
What was
answer.
the question?
Yeah. Oh, sorry. Let me repeat the question. So now we're trying to use the precession as a proxy to study dark matter. But obviously there are many other objects that can cause the precession or different kind of effect on the trajectory. So how do you differentiate that? So there are definitely many ways to do that. One of the way from the data point of view is that you have this data of all different A, for example, and different eccentricity. So if you want to extract out the dark matter contribution, then you need this to show up consistently proportional to this. So you should analyze all the data and extract this out. It's challenging, but it's not impossible. But another way to do it, so this is more like the data point of view. From the mission point of view, which I will propose, you don't want to mess with this because this is too noisy. You want to go out of the solar plane, and you have a dedicated mission, and which you also design it very well to go through the actually over density regime, and also you wanted to design the orbit that it's not too close and it's not too far, so the solar effect will be eliminated, and also you have enough orbit to track the trajectory. And thirdly, you also want to design it like a LISA Pathfinder to be the most non-sensitive to all the perturbation. But I will mention that later. Yeah. So, but the data point of view, you want to have a as fast as analysis to take into account this effect in order to extract that information? Thanks for the great question. Okay, so the OSIRIS-REx, of course, is tracking the Bennu, as led by LPL people. And it's very important because asteroid is dangerous. Actually, I just learned that there is a new asteroid found out recently that can hit us in 2032, I think. I forgot the name. But you know that
I don't know the
you don't know the yeah. But yeah, so we're in a lot of risk. And these people are really hardworking there. So what they do is that they will see some faint object on the sky because these things are not stars, so they don't have their own light. So they're very faint. So once you see one, you have to use all the telescope from Hawaii, from Asia, from Australia, from the US to track all of them, to track the trajectory to make sure we don't miss them. And also it's very important to also study the interstellar object. So there is a lot of excitement and importance to study asteroids and anything fly through nearby. And that's why we also landed on the asteroid to find out if there's aliens and weird virus that can kill us, or like expensive metals, or we want to. The most boring answer is we want to know the composition, so we know its trajectory better. But yeah, it doesn't sound as exciting. But yes, but one of the most important things is to know its composition, because once you know its composition, you know how much it will be affected by the sun, and you can know its trajectory better, and also know its mass better. Awesome. So there's a lot of detail, but we can get to a detail if you're interested. A lot of detail I'm still learning, but there's a lot of exciting things regarding how we study the asteroid. Okay. So a little bit more words on the Bennu data. This is kind of like a laundry list. So you have the ground base. So Bennu is so interesting because it's one of the most studied asteroid. You have the radar data, so including ranging and Doppler. So ranging and Doppler give you the line of sight distance and line of sight velocity. It gives you also the optical data, so it gives you the right ascension and declination. So you have two angles. And thirdly, you also have OSIRIS-REx tracking. So the precision is about 2 meters, and this is using some geometric pseudo ranging points. So you are constantly observing it, but then you use the observed data to do the analysis with the Earth to find out its distance and velocity. So you basically have all 6 orbital parameters that are available for a period of time, and it's summarized in this paper. So it's a very exciting object for case study. And the actual analysis, again, you have to consider all the planets. We consider 343 small body perturber. We consider the relativistic effect. We consider the ablateness. This is the easy one because this is theoretically predicted. This is the hard one. So the small body perturber is the bottleneck for the analysis. And also you have to consider ablateness, Yarkovsky effect, solar radiation pressure, Poynting-Robertson drag. I know a lot of people are expert here, so I will not get into detail, but you have to take into account as much as possible. And if you don't, it's dangerous, because if you don't, then you don't know where the asteroids would be, and maybe you'll hit us. So if we're missing anything, you should point it out so we can add it to the analysis. Awesome. So it's complicated. You add this simple dark matter term. And the idea, okay, so here is the money plot for this kind of snapshot of this current constraint. So rho max is the derived maximum density of dark matter. So ranging from 10 above the predicted above the average density to a lot. And these are just different over density. So let me go through this plot carefully. X-axis is the distance from the sun. So this is an AU distance. And you can see there are different planets. They provide a constraint on the over density. And Bennu is here, Apophis is here. And I also analyzed analytically 9 other asteroids to present you their current constraints. But let me go slowly. So as we mentioned, dark matter density is 10 to the minus 18 of the solar density average. But now our constraint can go to 10 to the 4 to 10 to the 7 over density, or 10 to the 6 over density. So it's actually a huge improvement. We have overcome 10 to the 12 to 10 to the 14 order of magnitude of precision. And this is exactly corresponding to a 10 to the minus 11 precision for the OSIRIS-REx. So this is a great achievement. And NEO is the near Earth object. You have high eccentricity near Earth objects, man-built and other asteroids. So you can estimate more different asteroids. And this constraint is radius dependent. So you kind of have a constraint on the profile as well, not just the one number. And yeah, and this is the value for Bennu constraint in terms of SI unit. What else I want to say? Yeah, any question for this plot? This is the most complicated plot. Yeah, please go ahead.
There's 2 points you haven't talked about, and I'm wondering if you're going to get to them. One is the pioneer effect, or rather the null pioneer effect. And the second is lunar range.
Yeah,
which I think would beat all of these things here.
yes, lunar ranging is very sensitive, but since in terms of precision, but sorry, I go too far. But lunar ranging is short distance. This has a to the third. So actually, in terms of constraining dark matter over density, this one is still stronger, and also it's a different structure. So if you use lunar ranging, you are constraining the over density near the Earth.
Whereas, but the pioneer thing is quite the opposite.
Yeah, pioneer thing is, I haven't analyzed the pioneer thing, so we should do that for sure. That one is, but that one is also not necessarily a closed orbit, if I understand. I think it's more like a hyperbolic. But
well, it's a test of any secular acceleration term whatsoever.
Right.
And the considerable amount of effort went into understanding that. In the end, it was a null result at an impressively high precision.
Yes. So
that's an integral over the whole solar system.
Right. So for sure, I think one should analyze that. I think the pioneer is the one. Is that the one that has a anomaly or?
Well, it had an anomaly, which is resolved. It
Right.
doesn't. It does no longer has an anomaly.
Yes. Yes. So yeah, I don't have the access to the data, but it will be very important to analyze that data for sure to see what the constraint it can provide. And I think so. If I get to know a lot of the orbital parameter, then I can also see where it fits in on this plot. Because for this one, so there are two things we can do. Oh, there's another question. Sorry, yeah, please.
Some of the things that you mentioned at the bottom of slide 17,
yes.
The direction of the force depends on what direction the object is rotating.
Yes.
So, and we usually don't know whether it's rotating clockwise with the solar system or counterclockwise.
Yeah. So for the Bennu, you have to take into account all of these effects. Bennu, you know which one is orbiting. But yes, there are some other asteroids you don't know, so then there will be a larger uncertainty. So I'm saying this one specific analysis is done for Bennu, but when you analyze other asteroids, sometimes that's why, for example, for Apophis, I think Apophis we also know, but eventually OSIRIS-REx, we will visit Apophis.
Apophis has more of a chaotic orbit, or a chaotic rotation.
Yes, yes. But I'm saying OSIRIS-REx will fly to Apophis to become the OSIRIS apex. So then we'll get more information. But you're right. That's why I put this as the blue color, because those are just some theoretical estimation. It's not a real analysis.
Okay. I misinterpreted your previous slide in that it was applying to the whole solar system and not the individual objects. Sorry.
Yeah. But we want to ultimately definitely want to do that. But definitely this is not enough for the whole solar system, because this 343 is the most important for Bennu. But if you go to asteroid belt, then there are all kind of messy stuff. So it's a difficult analysis to do. So we'll think about how to do that. But coming for the pioneer, I think it's extremely important to analyze the data. And we will also find out where it sits, because so pioneer is further away. I don't know.
Pioneer is tremendously further away.
Right. So it would be very beneficial actually. Yeah. So because the further away has actually benefits and also difficulty. So I want to talk briefly here because it's important. So if you're further away, then you have these induced precession effect that are larger. So a to the 3 will be much larger. So you potentially can constrain the rho 0 very well. But on the other hand, because it's further away, you also don't have like the closed orbit. So you rely on its trajectorial analysis, which is good. So that's something to analyze and to see how the precision of measurement it is. So yeah, any other question or comments? Awesome. So since I'm more on the theoretical side, so why are these currently important? So these are interesting in terms of setting a table for us to know how far away are we to finally find dark matter in the solar system. And as it turns out, it's not that far. It's 4 orders of magnitude, roughly speaking. But in reality, it's not that far, as I will tell you why it's not the case. But this is a benchmark. But even for these, we can already constrain some more exotic models. So in the particles theory or related realms, there are people who predict crazy overdensity of dark matter, and we also have other ways to probe it. But these are kind of soliton states formed around the solar system, so I have huge overdensity. And the only constraint, observational constraint, are these orbits. So these orbits can set a very strong constraint on this huge overdensity. As you can see, these are very exotic models, but it can have super huge overdensity because they are kind of like ultralight dark matter form a soliton, so it allows this very interesting bound state. Also, they allow self-interaction, so that's why it's so high up here. And you can already consider this kind of probe as one of the way to find these dark matter that have strong self-interaction, but doesn't have any interaction beyond gravity. So that, go ahead.
Soliton form because of the sun's gravitational field?
Yes, it's a kind of seed. So the gravitational seed first attracts some seed into it, but then the self-interaction allows it to grow faster. So there's a lot of detailed simulation for these, but I would have to say these are kind of the exotic model. But still, this is interesting model because you can still detect it without its interaction beyond gravity, if it's large enough, right? If the overdensity is large enough, you can observe it without any interaction beyond gravity. Right? And this constraint will be very important. There are also axion mini cluster from cosmology, solar basin from the sun production, solar production. And so there are all kinds of different kind of dark sector model you can probe with this type of trajectorial information. Yes. So this is not so important. These are bound state. Oh, another interesting thing is about neutrino. So if you consider the cosmic neutrino, then you can say that we can also translate this constraint into a constraint on solar neutrino. And this would allow us to constrain the solar neutrino to be the kind of number density of solar neutrino to be smaller than these comparing to the theoretical prediction. So it's 10 to the 11 times higher than the current prediction. So it's a very, very bad constraint. But it turns out it's as good as the Catherine constraint. So Catherine constraint is an experiment sitting there waiting for cosmic neutrino to hit it. And the constraint is 10 to the 11 over density. So you need the C nu B prediction to be 10 to the 11 higher than the prediction to see it. And it turns out it's the same order of magnitude as our constraint. So even though the planetary constraint is very bad, it's as good as the best one. So it means how hard the C nu B is to detect it. Yeah, it's very difficult to detect C nu B. But you can also view this as a constraint on the neutrino mass, which means neutrino mass has to be smaller than 10 to the 11 eV, which is differently a Nobel Prize winning. We know neutrino mass is very small, but now we have an actual constraint, which is, of course, there's many constraints. I'm just saying it's an interesting thing to look at, just to find out how hard it is to detect C nu B. Yes. Any questions so far? So finally, I want to briefly discuss the fifth force beyond standard model, and Pioneer will be also interesting to study this. The idea is that in the particle physics study, there are the sun and asteroids that people consider there can be long range force, kind of like a long range but finite distance force of this Yukawa type. When I say Yukawa type, it's kind of like a pion, but the range is very long. So you have an exponential decay when the distance is too long, but in the short distance, it recovers this 1/r potential, so 1/r square force. And this fifth force we can constrain again with this OSIRIS-REx study. And it's actually interesting, you can have a leading sensitivity for a certain period of regime, for a certain distance, because this is the distance that is corresponding to the Bennu distance to the sun. And this gives you the best constraint comparing to all the other constraints. And there are many different models that give you this long range fifth force, but for the interest of this talk, I'll just tell you that the analysis of this can also give you kind of long range fifth force constraint. And you can apply this to light, ultralight dark matter, fuzzy dark matter, and all different kind of dark matter candidates that can give you long range fifth force. Awesome. Because you are again affecting the orbits of the. So here's a summary before I talk about probably the most exciting idea. So the summary is that the GR test. So here's a summary of high energy theory target. Well, so you can do the GR test. GR will induce a precession kind of proportional to 1/8. And there's more complicated. And this beta, if this beta is different from 1, you have a deviation from GR. So a lot of the asteroidal study or space mission study is to constrain beta from NASA. But currently NASA is kind of getting tired of this because you can make it more and more precise. So you can always constrain GR better and better. But what's the end goal, right? So you don't really have an end goal. So it's harder to justify to NASA to continue this GR test. But now dark matter become more interesting because dark matter is actually a target. So you really want to try to study dark matter. And the behavior is also different. The dark matter is proportional to A to the third. So it's actually motivating you to study things further from the sun. And fifth force is proportional to A. So anything that larger distance could be interesting. So really, the reason why people only study planets, especially Mercury, is because if you want to study GR, Mercury is good enough. Actually, Mercury is the best because Mercury is very precise, very clean, and very well measured. But if you want to study dark matter or fifth force, then you should study things further away. So particle theory impulses are crucial, but it's also calling for modern data analysis approach to analyze all the asteroids. Okay, any question for these slides? It's a little bit complicated, but I try to, you can just look at the final parameter dependence. Okay, so yeah, there's 2 more summary before we go to the idea. So again, summary is that there are millions of asteroids you can analyze coming from near Earth 1 to Bennu, Hilda, Jupiter Trojan, trans-Newtonian object to extreme TNO. And there's also space mission like what is it called? Pioneer and other kind of space mission. There's also many space missions that are visiting the asteroids. For example, Lucy will explore Jupiter Trojan. LSST will see 5 times more of the asteroids. And OSIRIS-REx will visit Apophis. There will be the second version of deep space atomic clock, which I will talk about in the second part of the talk. So there's a lot of new excitement, and you can study many different type of particle physics / cosmology interesting topics, which I don't have time to talk about, including primordial black hole, modified gravity, dark energy model, monopole topological events. But what's the ultimate holy grail in this situation? I will give you 1 slide, but this is an ongoing project. I really don't just want to set constraint. I want to find the dark matter overdensity. So how do you do that? There is actually a predicted overdensity. So here, This is the galactic plane. This is the sun. And the sun will focus dark matter behind it because dark matter has a flow going through the sun. And this sun will focus the dark matter behind it. So there will be a focus spot. And there are previous simulation of where the focus spot is and how high is the overdensity. So the idea is we should design a space mission that can visit this spot. Either you do a direct detection, which is difficult, or you simply do the study of the trajectory of that specific mission. Say it's kind of like a LISA pass by. If we do this and we visit it several times, then we can potentially detect this gravitational effect. And then we can find dark matter in the solar system. So this is the ultimate holy grail to actually find dark matter in the solar system without any model dependence. But there is still a dependence in terms of mass because different mass actually give you different prediction. Of course, different model also give you different prediction, but I want to consider the most model independent type of model, the most generic. So, but different mass give you different prediction. So it's also a way to differentiate whether dark matter is wave-like or particle-like. So this is an extremely important project, but because it's a space mission, probably take decades to happen. But probably still earlier than Muon Collider. So we'll see. I don't know. It's hard to say, but it's always my joke. But yeah.
So where is this focus spot?
Yes, that's a $1 million question. So there are some previous analysis to say it's around here, around 0 to 1 AU. But the good thing is it's outside of the solar plane. So it's a cleaner place. And there are many motivations to go out of solar plane. So, and there are also predictions to the extended one. But these are wave dark matter of a certain mass. So yeah.
Oh, way back you mentioned that there was like a 1 over r squared term that you got rid of because it didn't affect, or at least you, I don't know, I don't think you're getting rid of it in the full analysis, but in the like precession only calculation, you would neglect that. But it occurs to me that like here, because it's out of the plane of the solar system, the 1 over r squared like effect of this displaced mass would matter. And I'm wondering if that's something that is important for this, or does it turn out to be way subdominant to like other you know, just the overall density contribution to affecting orbits?
No, that's a great question. This here, then the 1 over r squared term will be very important. Okay. And especially probably more important because you will actually go to that, right? So when you visit that, your 1 over r squared becomes very large. So that term will actually become potentially dominant. So that's why I say this is just a baseline. That's why I say this 10 to the 4 is just a baseline. In reality, it's actually much closer. So maybe we only have to overcome 1 or 2 order of magnitude because of this 1 over r squared. So, but of course, there's a lot of dedicated analysis to be done. But that's why I'm saying it's not impossible to find this. Yeah, please go ahead.
Right, so there's two things here. This is the exact same thing as a dynamical friction wake.
Yes.
And so it depends on the temperature of the dark matter. You know, it has to be pretty cold to see this. And I'm curious how cold it has to be and what is the overdensity that you actually get from this wake, because that's what really matters, is how much you amplify this over the background.
That's an excellent question. So exactly how cold it is, I need to actually do a proper analysis, but we can kind of understand. So
like CDM might be like 7 kilometers a second or so, or something like
right, that. This should be almost like CDM because these are simply the CDM being focused by the solar gravity. So I wouldn't expect the how do you say, the velocity dispersion to be much larger than CDM, but it requires some dedicated study, especially for the wave-like one. It could also be different. So this requires more study, but I wouldn't expect it to be drastically different from CDM. Yeah, and it would be great to check more because I haven't. This is just a basic idea. I haven't really thought about the whole detail, but it's very exciting to see. To at least first propose this, and then more people will have more clever idea to do this. Or just writing proposing a paper, but yeah, a lot of detail to think about. And there's also these are just minimal prediction. There are people predicting there are some strings passing through the sun. there are different things. So not the string theory string, like string.
Other
Sorry.
strings.
Yeah. Things like that. Yes. So there can be large over density, but those are speculated. These are the kind of baseline. Yeah. Yes. So anyway, and it's very important to simulate these over density predictions. So we're trying to do a more in-depth simulation, analyze large amount of asteroid data, develop a dedicated space mission concept. And if you're interested, there's a lot of things we should discuss here, and it's very exciting direction. Awesome. So that's the kind of first part. The second part is some kind of cute project. I can finish in 5 minutes. So I'll just see if there's any question. So how do we combine with quantum sensor? So quantum sensor, of course, we already know how to use it. With a very precise atomic clock, you can improve the precision of this tracking. But you can also do some kind of direct detection of dark matter. Of course, now you assume interaction beyond gravity. So we have this deep space atomic clock that you have very high frequency stability, and you can measure the frequency very well. You have the Parker solar probe. So why not put the deep space atomic clock on the Parker solar probe to find the dark matter over density near the sun? And that's exactly the idea. You put this atomic clock on the Parker solar probe, go to the center to experience this very high over density predicted by some more exotic theory. And the idea of atomic clock is that, let me go quickly here because I don't want to spend too much. Yeah. So you have this kind of wave-like dark matter that will oscillate, because for this classical wave, if you reduce its if it's cold, then it will oscillate in a way that, because their wave function are overlapping, they become classical wave. And for the very light dark matter, let's say much lighter than 30 eV, you become classic wave. And you can now experience the wave feature of this dark matter by looking at its oscillation and its effect on fundamental constant. Because when it's coupling to electron, you will have also induced oscillation for the fundamental constant. And the way to do it is you solve for this classical equation. It gives you an oscillating wave. The frequency is proportional to its mass of the dark matter. And then, because atomic clock can measure the frequency transition very, very precisely, so the effect on the oscillation of this frequency, you can measure with atomic clock. And this is also how we design time, because atomic clock can measure this frequency very well. Then we can determine what 1 second means. Okay. So the idea is that you have two atomic clocks. Both frequency are affected by the dark matter oscillation, because dark matter is interacting with the electron. So you have a certain coupling between dark matter and electron. It will induce oscillation. And this oscillation on the frequency also is induced differently for different type of transition. Whether it's, there are two types of clock I mentioned. Where are they? Yeah, maybe I missed that. Do I say it here? Yeah, for example, for hyperfine transition, this frequency oscillation is depending on certain parameter, Ca, and Ca is 0 for the electron dipole transition. So for different transition, you have different dependence. And now you measure this transition very, very precisely to extract out the coupling to dark matter, Ge. Okay, so that's the basic idea. So the upshot is that if you can fly closer to the sun, then you have an enhanced sensitivity for a certain mass range, because for this certain mass range, you have higher over density of dark matter. And you can probe some very interesting dark matter theory. Either it's motivated by natureness or some kind of cosmological motivation. And there's a lot of detail I will not get into, but again, x-axis now is the mass of dark matter, y-axis is coupling to the electron. So you can do this kind of direct detection using the space quantum sensor. Not just using the space quantum sensor for navigation, but also do active measurement of the frequency. And in the future, there will be nuclear clock. So you can also use a nuclear clock to do that. But I know here there's a very strong atomic, atomic and optical group. So this is the type of thing that could be interesting as well. Okay, and there are more different type of projection for the coupling to electron, photon, and here is kind of like a theoretical prediction. But we don't have to go into detail. It's just a different mass. And in fact, there's already constraints setting by the atomic clock on Earth, and it's this region. So there's already a lot of exploration on this. Any question for these plots? Yeah, please go ahead.
5 minutes.
Oh, okay, that's perfect. Yeah. So any question for this plot? This is kind of like direct detection aspect. And another thing we want to do, which is coming out soon, is we want to send a probe to Jupiter to study the overdensity around Jupiter. And it's a similar idea, but there we want to do a slightly different thing. So we want to actually measure the Jupiter magnetic field very precise. Actually, not really. We want to measure the magnetic field oscillation induced by dark matter there, and the dark matter has overdensity there. But then we have to worry about the Jupiter magnetic field. So how to do the shielding and all that is actually a very interesting problem. And there's also space mission to Jupiter like Juno. So it's very exciting to see how to combine this probe with those space missions. And going to the Jupiter is easier than going to the sun. So that's the kind of our current proposal. Okay, summary and outlook. So before our study, there's already a lot of exciting study for general relativity, modified gravity, planetary defense, and solar physics. But we want to add a lot more elements like study dark matter, cosmic neutrino, microscopic dark matter, macroscopic dark matter, topological defect, chromatic black hole, and all of these exciting things using the planetary defense data and space mission. And really, the elusive universe is at the horizon, and we have different unique opportunities today I talked about to explore it both with planetary, space, and quantum probe. And here are like two kind of programs that you can do. Either you do this trajectorial study or you do the direct detection. Both are very exciting. Thank you.
I mean, before we take question, I want to make a comment that I guess TAP have no problem finding topics that cover your two departments. Having a topic that your interest all three departments is unusual, but I think your talk is also interesting for optical science.
Yeah.
Cover 4 departments, that's amazing. Any questions? Yes.
So have you thought about Gaia data in this context? So you are getting precision astrometry for stars, obviously not as precise as what you can get for asteroids, but the value of A is also like very, very long.
Absolutely. Yeah. So people have mentioned that I haven't thought about how to directly analyze Gaia data, but Gaia data come in our analysis in 2 places. One is maybe it's too far away, so let me just think if I should go there. But so one thing about Gaia data is, do I mention this? Yeah, maybe just stay here. So there are many of these measurements, right? Gaia data kind of put a stellar reference point. So it actually help you to localize this faint object. So Gaia data actually significantly help improve the tracking of the asteroid data. So in the future, Rubin, like LSST5 more asteroid, you can use the data to have a more precise localization of this asteroid. So that's the indirect benefit. The direct benefit is there is this study of the overdensity. They claim there's a cosmic stream, like a stream of dark matter passing through the Earth nearby or solar neighborhood, and that somehow is supported by Gaia data. I don't understand that analysis very well, but there are these claims, so it should be further studied. But in terms of actually studying that trajectorial thing, I don't know if people do that, and that's because these stars are orbiting in a much larger scale. I don't think you have the detailed trajectorial information, but it's still worth thinking about. Yeah. For example, one thing that I've always wanted to do is to analyze the exoplanet data, because then you can study the overdensity of dark matter near the exoplanet. But of course, the precision is lower, but it's interesting as actually the original project was starting there. but then it's difficult. So we say, oh, let's do the solar system first. Right? But if you're actually expert from exoplanet, it would be great to discuss. Yeah.
You mentioned Juno at the end of your talk, and so what Juno data set is, do you think could be used to constrain this problem? Is it the length of the mission, or is it the precision of the tracking data? What is it that you would be looking at?
Yeah, so both are very interesting. So the Juno, in terms of precision tracking, in terms of the Jupiter orbit, is of course very interesting. But there's a specific thing we're looking at that we don't have actually too much expertise yet, but it's developing. So for Juno, so for this specific mission, what we want to do is we want to go near the Jupiter and measure the oscillation of magnetic field extremely precisely, because that oscillation can be induced by certain dark matter candidate. So then the Jupiter magnetic field environment will be very interesting. So Juno actually, I think, have measured the magnetic field environment. So to find that original data and find that oscillation frequency and do the analysis will be very interesting. And actually, people actually did that. There's a group in Brown, I think Gigi Fan actually studied the oscillation of the magnetic field using the Juno data to study.
Sorry, what do you mean by oscillation of the magnetic field?
So actually, time-wise oscillation,
I
kind of
mean, what time scale?
very short, depending on the frequency. So let's say, here, roughly 10 to the, actually not very, 10 to the 4. Yeah. So I know I saw the plot, the frequency that they are plotting is around the second-wise kind of cycle. But there must also be some data of the higher frequency, which I'm not familiar with. But I saw the lower frequency analysis. Yeah. So the Brown group, they did the oscillation study for the lower frequency. So it's corresponding to a lower dark matter mass.
I think some of that data was used to probe the different areas of different density within Jupiter itself.
Ah, okay, that's interesting. Because of the plasma?
I think they were trying to find like where the no, I'm not sorry, my mind is blanking on nouns right now. They are trying to figure out, I think, like where different areas might have like a higher density of mass and how the reverberations happen internal in Jupiter.
I see. That's interesting. Yeah, I'm not so familiar with Juno, but it will be something to look into more. Yeah. We already look at preliminarily, but not very extensive.
I might ask the same question that Bill just did for Solar Probe. What data sets from Solar Probe are helpful?
We haven't used actual data set from Solar Probe. We just put it as a conceptual thing, but it will be very interesting to study that. So let's just go through this. So the idea that we were proposing is very crude and very preliminary. It's just to say, let's put atomic clock on the Solar Probe. And since there are more dark matter around the sun, let's just analyze those atomic clock.
So my question is not necessarily a science one, but the way missions work. I would say Solar Probe was in the original 1958 Simpson report, and it didn't get launched until 2018. So 60 years or something, like 70, whatever. So going back to the sun is going to require another pretty big, and it's one of these, really high level class missions. It's almost $1 billion mission. So there needs to be a big reason to go back to the sun. Is there a push in the astronomy decadal survey to do this by any chance?
Oh, that's a great question. So I know there are several reasons outside of astronomy to do that. But there's so first of all, I want to say a few things about using the current Parker Solar Probe. So the current Parker Solar Probe is, as you say, $1 billion machine. It's kind of like the whole LHC throwing into the sun. So why don't we do more fundamental physics study? So actually we should, because there are particle detector already on the Parker Solar Probe to detect all the different information. Maybe you can use that to study some dark sector study. I haven't got time to analyze that. So it itself is very interesting. For the future solar probe, I think it will be very hard to. You need a lot of justification, of course. That's why we're doing the Jupiter probe as well. But let's say why else you want? I heard some defense reason. So they want to do an interesting thing. They want to shoot a solar probe to near the sun and then spread into many probes. And that somehow is a way to understand if one of our threats shoot down the satellite, how can you repopulate your satellite so you re-establish your Skynet? And somehow using the sun is a good way to do that. I don't know why, but there is defense reason to have more solar probe. Actually, they want more than one. They want many of them. They want to shoot one mission and then spread into many and to go around the sun. Yeah, but these are probably futuristic. But there are many reasons beyond astronomy that people want to do this. And in fact, the Parker Solar Probe is not really astronomy project. It's more like a helioscience project.
Yeah, it's a helio.
Yeah.
I'm a co-I on the mission.
Oh, awesome. Yes. So you know more than me, but for sure, I would say that any of these dark matter probe cannot be really a mission by itself. So you have to combine all the different ideas. Except I think if this estimation is really true that you can actually find dark matter in the solar system, maybe this one could be very interesting. And there are people developing like solar cell, all this type of thing. So I think it's interesting to just think broadly, to think if we combine mission together. But yeah, I agree that the next solar probe would be difficult to,
Well, it took 60 years to do the first one, so.
Yeah, but we should use the current data to see what we can learn already. Yeah.
That's great. So this is perfect timing. I guess Yu-Dai, you are staying until Thursday morning. So please sign up to talk to Yu-Dai. There is a special tour to the Applied Research Building tomorrow morning. So for the people who haven't been there, there is the new building across the way that you have a build space mission, you do all the lab work. I don't know if we can go into a lab to touch the space virus or whatever. But I think it will be fun, and everyone is welcome to join. We will leave at 10:15 from the student lobby, but we can also meet directly at 10:30 in the Applied Research Building if you're interested. I think that's all the announcement I have. Let's thank Yu-Dai again.